why we do so. The quiz is a retrieval test. Again, it's a very great way of cognitive learning tool to help you to hopefully push something you just learned into the long-term memory, right? So if you just prepare, like normally we do, until the end of the semester, you go over all the lectures and all the things you learned, will only stay in your working set memory, which is short-term memory, which will be forgotten just about 1 day or 3 days after the exam. So all the quizzes, all those frequent quizzes style and assignments, and hopefully other mechanisms, the projects, it's a way trying to help you to learn them more solid. So our goal is not just to get grades. I mean, I don't even care about the grades. I think much more important is you learn something very solid and also hopefully enforce those knowledge into your long-term memory. And then later in your job, in your research, it's very easily you can retrieve those important concept points or important pipelines we always trying to emphasize, like model selection, buyers and variance trade-off. And actually, to be honest, I feel they are more important than a specific algorithm, because the understanding about connecting different algorithms, it's actually much more profound than a specific algorithm. For example, deep neural nets, that's like a magic bullet, right? But you need to understand, when will it work? Maybe why will it work? But honestly, why it works is still a research question. It's extremely difficult to answer, and it's a very popular research topic. All the researchers trying to understand. So for people who just entered, we just finished the quiz. All right, so let's start today's lesson, which is extremely easy classifier. It has profound connections to the theorem I just said, buyers and variance trade-off. So again, we're in classification and learning theorems, and we learned about roughly what is supervised classification in the previous lesson, and what differentiate classification from regression is the output Y you treat it as categorical output, the set of symbolic outputs. You don't notice numerical relationship in the most generic setting. You actually don't model the numerical relationship among labels. Of course, from regression to classification, there's a big spectrum of something in the middle, something called ordinal regression, like sentiment classification. You're trying to predict 5, 4, 3, 2, 1. So rather than predict each one of them individually, don't think about 5 is more similar to 4, compare 5 to the similarity of 5 versus 1. There are a lot of flexibility and also dependencies among the Y's actually you can model to make the formulation better. So there are a lot of details, not just it's only classification or it's just regression. There are a lot of middle ground among these two extreme spectrum. And also we don't talk about when you have multiple Y's, right? So everything we covered is there's only one output variable, but there are a lot of cases you have multiple output variables. This really depends on the domains what you care, right? So for example, you care about blood sugar output, but at the same time, you care about maybe a patient's survival rate. Is this two output variable related to a clinical observations of a patient? And how do you model? And there's a lot of also other type of formulation in the middle too, when there are multiple different Y random variables. So, but in this course, when we talk about supervised classification, we primarily focus on still just only one output variable. All right, so we talk about we categorize the classification algorithm into 3 different groups. The first group is discriminative models. So the center idea is we try to model the decision boundaries. We only model the decision boundaries that separates classes. So we only model the decision boundaries. And the second category is called generative models. Generative model actually is, I'm trying to model the densities, model the properties of each class, and then using those type of modeling the properties of each class, and I try to compare. Is my future data more similar to class 1 or more similar to class 2 based on those density models of class 1 and class 2. And the last category is called instance-based classifier, which is the one we're going to talk about today. So the most classic approach called k-nearest neighbor approach. And this is almost the simplest form of classification because you basically have no model at all. So keep that in mind, no model. We don't learn no model, we just use instance as the model. So just roughly summarize, so the representation, actually what I should write it here is, the representation is the training samples. And using training samples, just the training samples, rely on local smoothness property, which is my assumption, to perform predictions of future data. So what the scoring function, what loss function k-nearest neighbor is optimizing is actually very tricky. So I will talk about it in the next lesson on Wednesday, but just roughly, it actually optimizes expected prediction error when using the L2 loss formulation. In the end, this is the best prediction because that best solution, if you optimize EPE with the L2, is the conditional mean. And k-nearest neighbor is exactly the conditional mean. So it will be more clear in the next lesson after we derive what's the loss function look like and why k-nearest neighbor is that solution. So again, who is the model in k-nearest neighbor? Training instances. There is no clear parametric model. The training instances are the model. So just to recall, we talked about the web pages. I mean, we represented them as backward word representation. Each is just the count of the words. So because the reason why I'm reviewing is the k-nearest neighbor homework in assignment 3 is to use k-nearest neighbor to classify movie reviews. And movie reviews are text. It's just text pieces. You're going to convert it. Well, actually, we already converted. We converted each text pieces into a vector form. That vector form is the size of the vector is the dictionary size, the dictionary you picked, and each entry is the count of the words appeared in a certain review article. And document 1, this is actually your first sample, second sample, third sample. And then you're just trying to, you have multiple classes. In this case, you're trying to figure out so this is just a speculated decision boundaries. So when you're using the k-nearest neighbor, actually you don't learn the decision boundary at all. You just have the training sample there. When there's a future sample come in, you try to check who is my nearest neighbor in the vector space. And you use the nearest neighbors labels to decide this future samples label. So this is one of the kinds of instant-based learning. It's almost the simplest form of learning because there's no model at all. Training instances are searched to look for those are mostly closed to your test sample, to your new sample, and the training instances is the model, is the knowledge. And the most important in this type of formulation is to figure out the right similarity functions. Because you rely on the similarity functions, to define who is my neighbor. So instance learning is also called lazy learning because there's no parametric model at all. You honestly, in the training phase, you do nothing. The most primary form. In the training phase, in the linear regression, you have a scoring function. You're trying to learn the best W and B, right? But when you use k-nearest neighbor, nothing. You really doesn't need to do anything. Question about this? I think I have a figure. Yeah, so there are different kinds of instance-based learning. There are k-nearest neighbor-based, and also there's weighted regression, which we skipped in the regression section, and also there are a lot of case-based reasoning in the knowledge-based traditional AI system. They're all belonging to the instance-based learning paradigm. So in k-nearest neighbor, you can think about just you can put them as a point in a Euclidean space, p-dimensional Euclidean space. The classification is done is delayed until a new instance arrives. And classification is by comparing of the feature vectors of different points. And target functions, it can be discrete or can be real valued, which means k-nearest neighbor can be used for classification. It can be used for regression too. So it's just this strategy, it can be used for classification if the y is symbolic. It can be used for regression if the y is real value. All right, so let's just see this. You have a set of data, and then there's a new data coming in, and you just check who's the nearest neighbor. If it's black, I'm going to treat this as black. And this is k equals 1, so I use holding the 1 nearest neighbor. So this is the blue points and my new points. If you use k equals to 3, differently, I'm going to, I should color this as blue, so, and you're going to look a bigger region. This is k equal to 3. So in this case, I'm going to classify this actually as yellow. So extremely simple idea, almost nothing, nothing to worry about. Yeah, question about this?
So the k should be 4, should be 4.
What should be k, right? Yeah, good, very good question. So the question is, how do I pick k? Yeah, so we're going to talk about it, and k is the hyperparameter, which is just like what you're coding for the polynomial regression and ridge regression, the lambda and the d. You need to search for it.
Why is this point classified as yellow, and how big the region should be?
So that's just because in the k-nearest neighbor, there are 2 yellow, there are 1 black. Sorry, I should color that as, this is the question point. This is my question point. It just, I forget to change its color. This point is my future point. And it's k-nearest neighbor, k equals 3, there are 1 black and 2 yellow. I'm using a majority vote because there are 2 yellow, 1 black, so that's why I'm using a majority vote. Yes, good question, because I did not even say, how do you decide, right? I'm using majority vote. Sure.
Do we only pick odd number, odd k?
Good question too. Yes, should I always just only pick, the question is, if I'm using majority vote, should I only use the odd number or I use the even number? Very good question. Yeah, I think it's a good recommendation to use odd number, but in fact, so there are a lot of variation of this method. Consider the distance check, which we're going to see later. So because, yeah, it's a good recommendation. So because you want to have a majority voting, right? So which you don't want to have a tie. And which means the odd number is more preferred because I always make a decision. So what you just mentioned has assumption. Whatever point I want to make a decision. But there may be cases I actually want to pick out the tie case, right? Those regions are very hard to decide. And those are the cases, if you force us to make a decision, it's also not necessarily good. Yeah. So we're going to talk about later. Okay? Sure.
So for this kind of instant-based method, the final result will depend on the order of this instance coming.
The order?
Yeah.
Good question. So the question is, this type of instant-based approach, is the decision depends on the order of the training samples. Depends on, do you formulate it as a batch learning or online learning? Because if this is not about online learning, your data just come all together at once. So all the training sample is there. So I understand why you asked that question is you're thinking about stochastic gradient descent formulation, right? So actually have a samples of the training data and the order really matters. However, when you do instance-based learning, in this primary setting, we just assume we have all the training samples already. We have all the training samples already, which means doesn't matter which comes first because there's no streaming process there.
Will the label of the test data affect the decision?
The label of the
Test data.
text data?
Test.
Oh, test. How could you know the label of the test data?
When if you have already made a decision in the first step and another you have a new data inside.
Great question. Okay, you all ask so great question. So the question is, do I revise? Because the question is, if I have a new test sample, I'm now predicting this as yellow. Do I keep that yellow in my training data, which means do I update my training data by adding that sample or not? This is your question, right? That's the other online formulation. So what you're saying is you're updating the training set. So the primary focus we are having now is, okay, we don't updating our training data. However, actually you can. That's just more advanced version. In this online version, assuming your data is coming in one at a time, and the distribution actually changes, you actually should add in the new samples if there are manual labelers. Keep providing the correct labels. And let's talk about it later. So just all is very advanced. So this is such a simple algorithm, but it's a very extremely flexible and versatile approach. We're going to talk about online setting later. Okay? All right. So what do you require to do nearest neighbor classification? It's three things. You need a set of stored training samples. So for example, here, I actually know where they are, all my training data. I know their labels, I know their positions. So here I mean their positions, which means I know their features. So equivalent to here, I know the stored training samples. Actually, this is my model. Nothing needs to be done. That's my current, that's my model. And then you also need to define what's the distance metric I need to use. I'm going to use when there's a new testing sample, a future data come in. How do I decide the distance or the similarity? They're just reversely proportional to each other. What distance metric to use? And this definition of distance metrics really relies on the domains. For example, in the text case, we normally use cosine. Cosine distance, cosine similarity. In the image case, we can use Euclidean distance, and then there are actually so many more different domains. They require different type of similarity functions. And then is the value k, right? What k do you use? And this k is extremely important, but for now, what I can tell you is you selected using cross-validation. Again, just like your homework, you have the training, testing, leave the test not touched. Have the training split it into either train validation or do cross-validation to loop over all the training data, and then using different k to get different validation error, then do argmin on the validation error indexed by the k, and that's how you got the best k. So a little bit of detour in the homework. So actually our true model d equals to 5. And when you're doing the validation loss, I hope you already reached that step, is this kind of loss curve versus the degree d. And you're actually not seeing something going up. You actually see something like a plateau. So you actually can just increase that d we give to you to even larger. You're going to see the up trend. But for everything we gave you so far, it reaches some kind of plateau. And it gave what it returns you, the smallest value, is not exactly 5. It's something very close to 5. So that's all correct. Don't get panic if your true model, the selected model is not 5. So there's a reason behind this, right? So very sorry, we actually, because we did not normalize data, then we later normalize data, then we figure out. So there's a lot of not very good software engineering when we design the homework is, so we'll give you this data. The data is actually very tricky to plot the gradient descent. If you do not do gradient descent, everything is great. I mean, normal equation give you the best solution, and everything is it just gave you the good solution. But just because I want you to have some kind of connection, thinking to connect the homework 1 by plotting the epoch versus the training and test era, then you need to try the gradient descent. The previous version we did not normalize it, and that makes the gradient descent extremely difficult. You just have to have super small learning rate and to have many iterations. So that's why we just normalize the data. But because we normalize the data, now your theta, your best theta you learned, it's a little bit difficult to figure out why that's even related to the true theta. Without normalization, actually it's super easy to check, because for the degree 5, that degree 5 coefficient is pretty large and significant. But for the degree 6 and degree 7, they are almost equal to 0. So even though we select the 7 degree as our best model, but actually those 6 and 7 got extremely small contributions in if you don't use the normalized feature. It's just a little bit complicated now. Sorry about it. So you can please, maybe you try unnormalized version. There's no way to try, right? Because we normalized it already. Okay, you know how to comment the code. So you generate a normalized version, you run everything using normal equation. It's very easy to tell the degree 6 and degree 7 got extremely small coefficient. And that's, you can tell it's very similar to the true model. But after normalization, that number got pretty large, but it's still relatively small than the degree 5. So this is a good exercise, to be honest, even though it's kind of chaotic. And yeah, so you can get the first sense how important feature normalization, feature scaling is to the solution. And also the differences of normal equation versus the gradient descent. Gradient descent is extremely sensitive to the data scales. This is a very good example to show you. Alright, questions. It's a little bit detour, but I want you don't get panic if you see your results so far from the true model. Because the true model is generated from unscaled data, unscaled features, and what you're using are scaled features, but you normally actually do use do feature scaling when you do gradient descent type of optimization. It's just to guarantee the convergence. Question? Yeah. All right. So So we have two, and this is the question future data, and then we just use k equals 3, and then very easy. You figure out that's also a positive. So this we just propose to use majority vote. When you have unknown data, you compare the distance to the training record, you identify k nearest neighbor, in this case 3, you use class labels of the nearest 3 nearest neighbors to do majority voting. This is 3 versus 0, so this unknown record will be classified as positive. Okay, so now let's change k. If this is 1, this x is the question place. Yeah, so let me make it more clear. That x position is the future data. I actually do not know. So, and when k equals to 1, it gives me minus. K equals to 2, it doesn't even know. K equals to 3, it gives me positive. So, what does this tells me? So if I'm going to train a classifier, for example, on this, it's highly likely I will train something like this if it's a global model. And honestly, this is not that difficult to figure out the classification boundary if I'm training a linear separation line. Hopefully this, of course, the points I'm picking is a bad point. It's at very close to the decision boundaries, right? So, but just the k changes and the decision boundary, you can actually try to get the decision boundary when you have different k. And I hope, let's go do that. So before I'm doing, because I'm trying to draw the decision boundary, let's go over the k nearest neighbor implementation. Because you are going to implement it in the homework 3. So we are given as what we always have, the first sample, second sample, onto the nth sample. And then each of this is first variable, second variable, onto the piece variable. And then you have the y, so this is your training data. And tr and train. Yeah. So when you have a new point, for example, let me use small x just not to confuse you. Let's use s, that's fine. Just let's think about that samples. When you have s question mark, it's a vector. So how do you do k nearest neighbor? I already told you, it should be super easy, right? Assuming I give you 3 things. Distance metric of a sample xi and xj, and use x. Yeah, let's use x. I give you 3 things, right? Sorry, yeah. Okay, so first I give you decision metric. Second, I give you the k. I think the third thing I should give you, the third thing I should give you is the training samples. So now, how do you classify?
Store each point and take the k highest ones. Or
You-
k
First,
smallest distances.
Find the distance.
yes. So first, I need to calculate the distance of x question mark versus x1, x2 until xn, right? Step 1. You need to get dx question mark versus x1, dx question marks versus x2 until dx question mark versus xn train, right? Oh, sorry. Then what? What's the computational cost of this? Let's assume we use Euclidean distance. What's the cost of this? Let's use big O. What is it?
Big O and train.
Big O, then,
Number of
and then, and,
features. Into features.
yeah. So the cost of this is O and train and P, right? Because the Euclidean distance is a summation of quadratic each element, and you have P elements. So it's MTR times P. This is the first step. Okay, who has question about that computational cost? Yeah, so assuming there's, let's do it later, but there's only one test sample. It's ONTR times P, right? Then what? I'm picking K out of this list. What's this cost? Pick top K from that NR list, right? Actually TR. What's this cost? This is your data structure class, right? I mean, 2150. Yes, this is the 2150. You should know this. Fast approach to get top K. N get K. What's the cost of this? Shout it out loud. What's the cost of this? Top K from a list.
You're in O then.
Oh, yes. Sorry, it's not top P, it's top K, but actually it doesn't matter that much. And I'm pretty sure there are better algorithms, but I think it's log TR or T. Let's use primary approach. Yes? And then you decide, right? Step 3. Step 3 is you perform y question marks equals to 1 over k, so summation of nearest neighbor y that neighbors it's my current nearest neighbor. Yeah. Yeah, sorry, just the handwriting is a little bit shaky, but I hope you understand it. So what I'm trying to show this is, so for every number, every y belongs to the nearest neighbor of my current x question mark, you use it to vote. But normally what you use to vote is from that equation. It's the simplest, really the simplest equation ever. Alright, so this is the simplest formulation, right, of possible classification. Let's see, if I increase y, what will happen? So this is, so we always just, let's do analogy. When you have doing the regressions, there's all those points, and you try to learn this or that. When d large, my complexity going up, right? So there's a really important idea called model complexity going up. When d goes small, my complexity going down. But for the nearest neighbor case, when k goes up, how do the complexity changes? K goes more, there are more and more neighbors to be considered, which means my model is actually less and less complex. So this is very important, even though it's very intuitive, but make this analogy, its complexity going down as the k goes up. When the k smaller, the complexity going up. Okay. Your ridge regression task, when the lambda goes up, how do the complexity changes? When your lambda increase, how did your model behave in the ridge regression? When the lambda goes up, complexity going down. So when you plot your figure in the ridge regression, we have this lambda from small to large. Complexity going down. Who has question about this? Because this is very confusing actually. When lambda goes small, so in the ridge regression homework, the true model is there's only one feature relevant, all the other whatever features is not relevant. When your lambda goes up, you penalize all the rest of the irrelevant features to be not important, which makes your model concentrate on the relevant features. It's a much simpler model. When your lambda goes down, which means I consider all whatever number of features, my model is extremely complex. So that's my complexity going up. So when you plot your data, you're going to see something, the training, I think it's a test area, training area goes up. So think about it, it's actually, I'm going to talk about later. So normally when we plot something called bias and variance, like the figures, we all have this complexity, model complexity from small to model complexity large. And the ridge regression, if you plot it from smaller number to big number, actually you flipped it. What you're plotting is from large complex model to small, not simple, not complex, simple models. Keep that in mind. Okay, don't get confused if that figure you plotted is so different from the normal Bayes and Barron trade-off figure. Yeah, so you really just, you need to understand this, the trend. K is, so in the k-nearest neighbor case, in the ridge regression case, and in the polynomial regression case. So it's d from small to, the direction is d gets large. And the ridge is the lambda complexity going large as lambda gets small. In the k case is model complexity at large as k goes to small. Yeah, okay, question about this?
I didn't understand why does model complexity increase as k decreases?
Oh, why model complexity increases as k increases?
As k decreases.
Oh, k decreases. Yeah, good question. So I thought I wanted to talk about it later, but let me show you this figure. Yeah, okay. This is exactly why. So when you use k equal to 1, your model, a classification model, because it's hard for me to directly draw that, the classification boundary will look like this. When you use k equal to 15, it's much smoother and has some kind of certain shape. And this is what I meant. This is less complex compared to this model. Question about this? In the end, the bigger k you consider, the more smoothness you assumption you enforce about all the neighbors. You assume all maybe k equals 15, which means I have assumption whenever at 8 points there are 15 neighbors of each other, they should have the same labels. That's my assumption. This is a very strong bias you added onto the data. Yeah. All right. So sorry, I should move that figure. I'm going to revise my slides, so to move that earlier. So now we finished about the algorithm, and I think you should be able to implement it very easily. And now let's see. I have m samples. I have m future samples, and I have to multiply everything I'm doing here by a n, right? So there should be m times ntr, m times ntrp, and but this is quite negligible because this is only related to k, but you still need to do m predictions. So keep that in mind. Yeah, sorry, I used to do this, and now let's see what this 1 nearest neighbor is doing. So 1 nearest neighbor in the end, when you have 1 nearest neighbor, because this is my model, right? Essentially, it's trying to learn, it gives the decision boundary, even though it doesn't have explicit form of decision boundary. It defines decision boundaries by really, so if there's 2 points, the vertical lines separated, the 2 points, the connected edges, is the decision boundary. It uses something called a Voronoi diagram. It essentially segments the whole space using the Voronoi diagram. And it's segmenting the whole space into disjoint subspaces. And if there's some kind of noise, you can actually tell that neighbor defined by that specific point will be totally influenced by the noise labels. So this is trying to show the 1 neighbor case, this is trying to show the bigger neighbor case. If k is too small, it's very sensitive to noise training point. If k is too large, The neighborhood may include many things, so it's just super smooth. It's not very flexible if you have too bigger K. Yeah, we have the point there, so I think I already emphasized this many times. X small, it's very flexible, it varies a lot. The decision boundary varies a lot. When K is large, it's very smooth, it varies very little with the changes of the training samples. So related to what we just mentioned, the k-nearest neighbor, it's because it's a distance metric, right? And then it's pretty sensitive in the end to the scaling issues too. So assuming you're trying to predict someone is diabetic using the height, ages, weight, I mean, if you do not do the feature scaling, it will be very problematic, depends on what you use to represent it, right? With, for example, the weight, it's normally using like 90 to 300, and the height, if you do meters or if you do inches, they are mostly pretty small number. And also like maybe income is also an indicator of they're diabetic or not, so you can also use those numbers. If you do a calculation of Euclidean distance on this, and the whole thing will be very dominated by those feature variables has larger values. So in the end, to this distance metric, so it's better you actually do a feature scaling, just like what we did in the homework. We provided you with the feature variable already being scaled into mean zero, right? We did a mean zero standard deviation 1 feature scaling, which makes the distance metric of actually the gradient descent too. They all suffer from this type of numerical issue. If one feature variable or a few feature variables is so large, the number is so large, those feature variables will dominating the less larger the other feature variables. The mean or standard deviation is much smaller or much more coherent. So this is a very tricky issue, actually not just for nearest neighbor. It's for gradient descent, for actually SVM, for almost every I think deep neural nets also needs to scale the data. If actually you should scale the data too. So it's just an empirical trick. So you can of course use it for regression. So because that final step y question mark goes to 1 over k, summation of j belongs to the neighbors of k nearest neighbors of x question mark and yj. It's not just for the symbolic labels, it also works for numerical value too. So k nearest neighbor is a natural also a regressor. You can also use it for regression. So who has question about this formula?
So how are we predicting the y value if it's a regression case?
Good question. So the question is, so in a classification task, how do you decide? Because this gives you a numerical value, right? So assuming we have two classes, so our classes belongs to, we have to convert it maybe into 0, 1. So all the y belongs to 0, all 1, right? And then you calculate, if you do majority vote, it doesn't matter. It's not a symbolic output. But most cases, actually, you do this numerical operation to reflect the symbolic operation. If it's 0, 1, you're going to get maybe from 0 to 1. How do you threshold it? It's a very tricky question, actually. It sounds super easy. It's actually very tricky. So what is the majority vote threshold? If I'm using majority vote, what is my threshold? I'm doing majority vote. Equivalent to I'm using some threshold to thresholding y question mark. the threshold, what I meant if y question mark larger than some values, I'm going to predict it as 1, the plus 1 class. If it's smaller than some threshold, I'm going to predict it as class 0 or class minus. So majority vote means I'm using what threshold? 0.5. Yes, majority vote, right? 0.5. Yes, but just related to the question we tried to emphasize before is if you're handling a extremely unlabeled, unbalanced data, if you handle extremely unbalanced data, if you use 0.5, it's highly likely you're going to always predict everything into that majority class, whoever is dominating. It's just a natural preference, right? Using 0.5, it will be always dominated because the density, because that class is always like 99% dominating whatever regions, or maybe most regions. So it's very tricky to figure out the T in the unbalanced cases. Of course, in balanced cases, you can just 0.5. And there are many actually, like 20 years before, people designed how to figure out the T. Cost sensitive. I think one of the questions we actually ask you about this, it's almost in that direction. You can try to optimize something called precision, maybe top 5 ranked, and you can design accordingly the scoring function, and then hopefully by it's the later than when if you do a parameterized model, rather than optimizing the whole accuracy, you can optimize the top 5 accuracy of something later. All right, so let's see the nearest neighbor, the Bayesian regression. Sorry, I'm not going to repeat it. So this is a little bit confusing. In the end, it just there's one-dimensional x and y is the output. So if I'm doing a 5 nearest neighbor regression, what I'm going to learn, so here it's not classification. There's no blue or black, right? What I'm trying to predict is really just a middle curve. I'm trying to predict y. So this is not classification, this is regression. I'm using the mean. If you think about it, whenever, so assuming this is a point, there's a point, I'm using the nearest neighbor 5. I think if I change it there, my nearest neighbor maybe should be this 5. So maybe more dramatic, this is my current question mark. I'm using the distance on the x, not on the y, right? I'm using who is my nearest neighbor, I think is 1, 2, 3, 4, 5. Yeah, this is my nearest neighbor. So this 5 points are my nearest neighbor, and I need to use the mean. I use the mean of this y, that y, and this 4th y and 5th y to decide the y of my new points. This is what I meant, conditional mean. Conditional on the neighbor, I calculate the mean, and this is exactly the equation conditional mean. Okay, question about this? All right, so yeah, of course, this is the Euclidean distance, but you can have many other type of distance too. You can use cosine, which we introduced is just a special case of Pearson correlation by using the x bar and y bar as 0. So I hope you still remember or already learned that in your text mining or information retrieval class. And yeah, so I think that's about it. And then there are variations is, so rather than using the y, so the all previous y question mark equals to 1 over k summation of and then the y directly, right? So rather than doing that, actually let's do something like this. yj. J belongs to nearest neighbor of, actually k nearest neighbor of x question mark, and then I'm weighting that y by using the distance. Should I use similarity? Yeah, I should use similarity. Y minus t. Yeah. So this actually using something like W. It's a bit easier way to write it. Wj, and here Wj equals to 1 over d, that specific xj versus my x question mark. So if this xj is so close to, so similar, the distance will be small and the weight will be large, which means the more similar, more close of the x question mark to that nearest neighbor, this weight will be larger. It's equivalent to the more close to my x question mark, the more contribution, the more decision relies on that specific yj. This is called a weighted nearest neighbor approach. Actually, there are many variations of this. This is just only one kind. Question about this? Nope. Okay. Yep. So if you think about it, I think this is the next page. Yeah. So, yeah, I should put it there. You actually can replace that w with the radial basis function we learned in the basis function expansion before. We replace that w through a kernel function. If you still remember what is the kernel function. The kernel function is centered at that specific x 0. So in our case, it's our x question mark. It give you values like, you know, a bell shape. Sorry. So the center, it give you 1. If you go minus sigma, it goes to 0.97. If you go 3 sigma, give you 0. If both left and right. And this is a very natural weight function because the more close and the more contribution, that specific yj, let me use, because I use j all the time, that specific yj will contribute more. If it's really, really far, it will contribute less to my current prediction. And in the end, actually, you don't even need to calculate nearest neighbor in this formulation. You actually can just use the kernel functions to calculate that value over all the possible training data, and then decide what is my current. So you centered RBF basis on my current y prediction, y question mark data, and whoever is close to me, that weight, it decides by this bell-shaped function. If it's really close, it's weighted by those bell shape. If it's really far, it's not going to contribute at all. And then this is a natural classifier. This is actually called a natural regression, which we skipped, called local weighted regression. It's a regressor. It's a non-parametric approach because the number of parameter, which is actually wi here, if you think about it, wi is a parameter. It grows with the number of training samples. So we're going to, don't worry if you don't understand it. So think about this as an extreme case of k-nearest neighbor. It's an extreme case of weighted k-nearest neighbor. Rather than calculate the d, xi, xj, I'm using this bell-shaped function to decide the w. And the bell-shaped function pushes everything outside the plus and minus 3 sigma to be 0 contribution. questions about this? So this, you can think about because it's extreme weighted k-nearest neighbor. All right. So now let's come back to compare linear regression or the versus k-nearest neighbor based regression, which I waited for a long time. So in the training, if you still remember, the cost of training a linear regression is ONP quadratic plus P cubic. And in the k-nearest neighbor case, it's O1 cost because there's nothing you learn. In the testing phase, let's just see only one sample. In the linear regression, your cost is OP. Who has question about this? The cost of linear regression or linear models is OP. It's only related to the size of the feature. However, in the k-nearest neighbor-based approach, it's polynomial to the size of the n. Of course, it's also size to the p. It's also actually this is a more dominating cost. Because for each training sample, for each test sample, you need to calculate the distance measures, and that distance measure is proportionally increased with the size of the training data. So, who can tell me why is this even bad? We are saving the training cost, right? Saving largely.
We want less testing time instead of training time.
So even though, so the answer is we want to have less testing cost. Of course, right? In a lot of situations, assuming there are streaming cases, there are real time, because this is the deployment cost. This is when you truly deploy the software you just learned into the wild real cases, and that's the cost. And you don't want the cost to be proportional when you have more training data and you can keep increasing. And also this is a pretty large number if, let's just assume, in a lot of cases, maybe text cases, P equal to 30,000. N equals to maybe 30,000. This is even not large for the state-of-art news classification, assuming only 20,000. But if you think about Google scales, the Google scales maybe 2 billion points in the N, right? How can you even make this even for one sample? The cost is ONP. So in the end, k-nearest neighbor is extremely simple algorithm to implement. However, it's extremely difficult algorithm to make it scalable. And there's actually a lot of state-of-the-art tools to make this search faster. I'm not sure if you ever learned about KD tree, ball tree, and all this type of data structure, tree-based data structure. It tries to organize the NP and space into some kind of data structure. So rather than search ON, you try to search a subset of ON. You don't search all the N training samples. You actually search only a subset of the training samples. So there are a lot of tricks actually you have to implement or use if you use the k-nearest neighbor approach in the real world system.